Good afternoon, everybody. I am Yazan Alrefaei, and today I'm going to introduce you my master thesis research work, which has been conducted in Kuwait University. Well, the title is already shown here on the first slide. So basically, we're going to design and study the structural behavior, especially the shear behavior of the beams whenever it's used, whenever it's made using a special material, which is the hybrid steel polyethylene fiber reinforced cementitious composites. Well, at the beginning, we all know that the idea of using the fibers itself, it's not really a new idea. It has been used before by ancient civilizations, as you can see here, like the Egyptians and the Greeks and so on, who has been using fibers and hair hoses to reinforce that mud bricks in order to build their own homes. However, this addition of fibers is being done in order to increase and enhance that tensile response of such a brittle material. Well, why we do use steel and polyethylene fibers? Because these two types of fibers, they are most favorable options in research because they are less susceptible to the environmental attacks, and because they are available in the markets and they are relatively cheap. So that steel fiber, actually, it has been recently limited to use on structural applications by the American Concrete Institute, and there's so many research right now going on these materials. Well, the idea of hybridization by itself is just by adding two different types of fibers together so that we can make benefits from each type individually. Well, recently, ECC materials, which is engineered cementitious composite, this has been used as a protective material with polyester hardening, and there's so many applications, as you can see here, regarding these materials. Now, we want to apply this ECC material with hybrid polyethylene and steel fibers to study the shear behavior. Why? Since this material is really have a high ductile polyester hardening behavior, and because we all know that the shear failure is highly brittle and it's catastrophic, since it's happened previously a collapse in the US Air Force. So we want to apply such a material with a high strain polyester hardening and study that shear response of such a material. So in this program, actually, 6 beam specimens has been casted and tested under A/T ratio of 3, which is the shear span over the depth ratio. And the mixed proportion used was already adapted from previous research. As you can see here, here is the 6 beams. The first one was control beam with no fibers at all, while the rest have a combination of hybrid steel and polyethylene with maximum volume fraction of 2%, as you can see here. Okay? Well, and this is the mixed design, as you can see. Well, the material used in this research was already in accordance with the ASTM with every aspect. And here's the properties of the fibers, as you can see, and here's the picture. This is the steel fiber, and this is the polyethylene fibers. And they have the same length, almost. And the reinforcing steel bars used in the beams also was tested and conducted under the ASTM. Well, we have cast some non-fibrous cubes, and we have cast fibrous cubes, and as you can see here, we took special care when we cast such a material because this is relatively new material which has not been applied previously in the site. Well, all specimens again was huge for 7 days, and the test was conducted at the age of 14 days. And this is the schematic figure that shows the beam details and the cross section and so on. And this is the loading condition that we use. Now let's jump into the results and the conclusion, which is the most important part. First, I would like to show the relationship between the compressive strength of the cylinders and the hybridization ratio between polyethylene and steel fiber. Well, generally, increasing steel fiber in that ECC composite slightly increased that compressive strength. So this increase was a little bit shy, it's not that much increasing, and actually this result was inconsistent with the previous research, as you can see here. Also, another relationship See, it's plotted here in figure 4, which is the relationship between the tensile stress, the slip tensile stress, and the hybridization ratio again. So as you can see here, increasing the steel fiber and that composite actually slightly increase also the tensile split strength. However, once we reach that 1% of steel fiber, no extra enhancement has been noticed after increasing the steel fiber above the 1%. Okay? And again, if you control, this is the relationship of the hybrid fibers. If you control it to the control specimens, which is non-fibrous, we can see that it has been increased more than 2.5 times. Again, you can see this thing here. So the tensile split strength has been increased between 2.5 to 3.5 relative to the non-fibrous material. And again, this result was inconsistent with previous research work, as you can see here. So Kuchara in 2003, he said that adding 2% to steel actually may increase the split strength by twofold. It means 2 times, as you can see here. Okay, now let's jump into the response curve. This is the response curve. It's been drawn, the relationship between the applied load and the deflection. It means load deflection curve of the specimens. Well, at the first, if you want to compare, these are the hybrid beam, and here at the end you have the control specimen. So first, the stiffness of the all hybrid beams was higher relative to the control specimen. This is number one. Number two, also, we can see that increasing the steel fiber and the steel in the beam actually slightly increase the stiffness of such a beam. Why is that? Because the steel fiber have a higher modulus of elasticity compared to the polyethylene one. And we have also noticed that all the beams have extended yielded plateau. As you can see, it have extended yielding plateau, and also some of them they already filled in shear, so they have large basilar strain hardening. Again, we have calculated the theoretical flexural strength of the beams, as you can see here. This is the flexural, the strength, the theoretical flexural strength of the control beam, and this is the theoretical flexural strength for the 2% steel beam. All of the hybrid beams have exceeded this theoretical strength, as you can see here. Now, we are studying the shear behavior. So, when I block the shear stress against the hybridization ratio, which is the polyethylene and the steel, for example, at this point, it means that we have 1% steel and 1% polyethylene, as I said, because the total volume is 2%. So here, as you can see, for the shear stress, actually, we didn't notice any trend because all the hybrid beams actually have approximately the same shear strength relative to each other. However, this beam here, which was 2% steel and 0 PE, actually this one, it failed in flexion, while the other failed in shear. So this value should be equal to or larger than this one. However, if you compare it to the control beam, you can see here that it has been increased more than 8 times. Now, let's look at the cracking behavior, because the ECC material, it had actually multiple cracking behavior with basilar strain hardening behavior. So as you can see here, this is the control beam. The control beam actually, it have the typical shear failure with one single crack, one single major crack. Actually, this one, it has happened because of the extra loading at the end. While the other fibrous beam, as you can see, all of it have multiple cracking behavior. And again, what we can notice here, actually, that this is the higher the polyethylene volume included in the beam, we have a higher multiple cracking behavior. So in decreasing the polyethylene volume will lead to decrease the multiple cracking behavior. So here we have higher multiple cracking behavior and so on. And as I say here, this one, it have 2% steel. This one, it was the highest strength and it fell in flexure, not in shear. But if you compare the tensile, the shear cracking, here we have lower shear cracking than here because polyethylene volume here is 0 approximately. So we got the relationship between the crack spacing and the hybridization ratio. The crack spacing was calculated by dividing the distance between each crack over the number of cracks minus 1. And we have got this relationship. So as I say, increasing the polyethylene the polyethylene volume fraction leads to extra multiple cracking behavior, which means that the crack spacing will be lower and lower. So increasing polyethylene volume leads to a decrease in the crack spacing. So at the end, let's make the conclusion that the use of ECC materials in the beams actually enhanced the shear strength. Why? Because it enhanced the multiple cracking behavior and it enhanced the strain capacity relative to the non-fibrous beams. Again, the shear strength was increased up to 8 times, as I previously mentioned. So all this research and findings actually, it proves that using that ECC materials in structural application is really a good advantage in structure. So this is actually just a brief of my research work. If you want to see the full research work, it has been published recently in Journal of Structural Engineering. As you can see here, Journal of Structural Engineering, it has already been published and accepted, and we have already a conference paper from that one. Anyway, you can check this paper, and this is the DOI for such a paper. You can have a look. The full detailed laws is available there. And thank you all for listening. I hope that you have enjoyed that. Bye-bye.